scientific death.
We exist in a highly sanitized, predictable environment. We carry pocket-sized supercomputers, communicate globally without a second thought, and rely on an agricultural system that silently feeds billions. But this seamless infrastructure obscures a harsh reality. The chemical building blocks running those systems had to be wrestled into submission. If you step back into a 19th century chemistry lab, you don't find a sterile theoretical science. You find a hazardous, chaotic frontier filled with unknown, highly reactive materials. Mapping the periodic table required a brutal physical toll. Pioneers surrendered their vision, their lungs, and their limbs to pull secrets from the Earth. To understand how we achieved the precision of a modern microchip or the massive scale of industrial farming, we must look first at the explosions and poisonings of the people who built the foundation. Take the year 1811. The French chemist named Pierre Louis Dulong was experimenting with chlorine gas and ammonium chloride. He successfully isolated a new substance, an oily yellow liquid called nitrogen trichloride. As the discoverer, Dulong had no way of knowing it was violently unstable. The liquid detonated in his hands, completely destroying one of his eyes and blowing off two of his fingers. Instead of burying his findings, Dulong warned his colleagues. Sir Humphry Davy, a prominent English chemist, received the warning and immediately repeated the synthesis. The mixture exploded again, driving a piece of glass straight into Davy's cornea. Davy's temporary blindness left him unable to work alone. He desperately needed an assistant, so he hired a young, relatively unknown bookbinder with an interest in science, Michael Faraday. Faraday wasn't spared either. While holding a small tube containing just 7 grains of that exact same yellow oil, it exploded again. The blast tore away Faraday's fingernails and burned his hands so badly he couldn't use them for months. A single, terrifyingly volatile compound nearly killed its creator, blinded one of the era's greatest scientists, and directly launched the career of another. Explosions were visible and immediate, but other elements presented an invisible threat. The attempt to isolate fluorine gas became one of the deadliest pursuits in scientific history. The were severely poisoned, leaving one bedridden for 3 years. Pierre Louis in Belgium and Jerome Nichols in France both inhaled the toxic fumes and died. George Gore survived a massive hydrogen fluorine explosion by pure luck. It took decades before Henri Moissault finally isolated the element in 1886. He succeeded, but only after enduring multiple rounds of severe poisoning that shortened his own life. Securing a single new entry on the periodic table required surviving an environment that more closely resembled a battlefield than a modern laboratory. Even the elements that didn't immediately detonate or poison researchers harbored strange, destructive physical behaviors that could ruin critical infrastructure. Pure tin seems entirely stable, but when the temperature drops below 13 degrees Celsius, its crystal structure slowly degrades. The ductile, silvery metal transforms into a brittle, non-metallic gray dust, a process known as tin pest. Historical accounts suggest this elemental quirk devastated Napoleon's army during the bitter winter of 1812, as the tin buttons on their uniforms literally crumbled into powder in the freezing Russian cold. Then there was phosphorus, an element deeply embedded in the history of explosives. Highly reactive and known for its deeply offensive smell, it was quickly weaponized into the first chemical warfare agents. Science in this era was a continuous, brutal campaign against raw earth materials that absolutely refused to be categorized, predicted, or controlled. Today, we no longer approach these elements completely blind. We have engineered their violent tendencies into the tightly controlled processes that sustain human life. This digital flowchart maps the contact process, our industrial method to tame sulfur into sulfuric acid. Sulfur dioxide gas moves from the furnace through a specific sequence of scrubbers, drying towers, and heating chambers to safely yield the final corrosive product. Combining that industrial acid with thousands of tons of mined rock yields phosphorus and sulfur in the stable, accessible forms required to feed humanity. The exact same element that fueled early explosives and choked scientists is now the fundamental anchor of global agricultural stability. We see a similar mastery in digital technology. This schematic shows the cross-section of a silicon crystal growth furnace, where unpredictable atomic structures are forced into perfect, flawless alignment. We cleanly layer compounds like indium tin oxide in sterile cleanrooms to manufacture smartphone screens that are both highly conductive and perfectly transparent. We harness gallium nitride to build the light-emitting diodes that safely and efficiently illuminate our cities. None of this arrived cleanly. The foundation was bought with the ruined lungs,
blinded eyes, and lost fingers of researchers like Dulong, Davy, and Faraday. Every time you tap a touchscreen, turn on an LED, or eat a mass-produced meal, you are interacting with a monument. It is a monument built by pioneers who walked blindly into the explosive unknown.